Okay, as I said, Green's theorem is one of the neatest things in the world. The only things neater than Green's theorem are the Stokes theorem and the divergence theorem, which kind of follow from Green's theorem. Okay. And what Green's theorem tells you is that if you got a region and you want to integrate a function over the region, you can do an integral around the boundary and find out what the integral is over the interior of the region. Okay. Or if you want to find the integral around the boundary, and that's an ugly integral, and the integral within the region is pretty, you can do that. So it gives you two options for doing these integrals. And it's kind of amazing. Now, when you really understand it, you see, okay, yeah, any idiot could have figured that out. But what's going on? Okay. So let's just start with the idea, the Green's theorem. Let's just set it up. First of all, you have a vector function f of xy equals p I plus qj. The integral of f of xy dot dr, where r is just xi plus yj, right? So you would maybe write that r equals xi plus yj is going to be the integral. Well, it's pi plus qj dot xi plus xj. And dr is, well, we'll write it out, pi plus qj times dxi plus dyj. Are you with me so far? That should be kind of familiar stuff. You've done line integrals. Homework I've seen looks pretty good. Okay. Haven't seen it all, so if you haven't gotten it to me, get it to me. That would then be the integral p dx plus q dy. And let me emphasize that f is a function of xy, so p is a function of xy, and q is a function of xy. I haven't written p of xy, q of xy, it clutters up the notation a little bit. But there it is. Okay. Now we want to talk about specific cases where you integrate this around some curve. Okay. Now you know if f of xy is a conservative function, the integral around any closed curve is going to be zero. If the integral around on any curve is only going to depend on the endpoints. That's what you did in section 6.3. Okay. So in general, this won't be a conservative function. If it is a conservative function, you already know the answer. Okay. But we're still going to get something about the interior of the about the integral of something over the interior. We'll see what that something is. Okay, now I'm going to start here with a point xy and the point x plus delta xy and the point x y plus delta y and the point over here plus delta x y plus delta y. But we regard delta x and delta y as being small increments. Okay. Then we could have a z. We don't really need z, but this is, I'm hoping this will put it into context. It'll be somewhat familiar to you. So z equals f of xy. Then at the point x plus delta xy, z equals f of x plus delta xy, which is approximately equal to f of xy plus what? Plus fx delta x, partial of f with respect to x times delta x. That's what the differential is. That's what it means. And if that's not totally clear to you, it really needs to be. Okay, something that, an idea that you should theoretically have been developing for the last 18 months. Since the first time you saw a differential in calculus and used it to approximate, let's say, the square root of x near x equals 4. Okay? Using differential approximation. It's just the differential approximation. And all this means is you're taking the value here and then between here and here. Well, at this point, x is changing at a certain rate when you move in this direction. That's what fx is. Okay? It's the rate at which f is changing with respect to x as you move in the x direction. And that's a concept you're really going to want to have solidly in your intuition and your ability to manipulate by the time of the final. Okay? So you really want to ponder that. Make sure you really understand it. This is the rate at which x is changing, and this is the rate at which f is changing with respect to x, and this is how much x is changing. That's how much then f is going to change. Multiply its rate of change by the change in x, you're going to get the change. Up here, z would equal f of x, y plus delta y, which is approximately equal to f of xy plus fy, delta y. It's equal to what it is here, plus how quickly it's changing in the y direction by how much you change in the y direction. Okay? It's the rate of change times the change in y. And of course, you could write an approximation up here. And I'm just going to write what the approximation is. It's approximately f of xy plus fx delta x plus fy delta y. As you shrink toward the limit, if this is a decently behaved function, then all these approximations will approach exactness. Okay. Now, if I'm doing line integral around here, of just the function f, not the vector function here, but I'm doing a line integral, just some function little f of xy, which has nothing to do with these functions. I'm just doing this as an illustration to make a really important point. Okay. What's the difference in the value of f between this point and this point? How much does f change between here and here? Well, how much did it change between here and here? How many of you see? How many of you can tell me? I don't want you to say anything because we're recording. How many can tell me between here and here what the change is? Approximate change. Okay, not one person indicated they can. Anybody else? Well, let me ask you, how much did it change between here and here? By this much, right? It was f of xy down here. Up here, it's f of xy plus fy delta y. How much did it change between this corner and this corner of my rectangle? Well, change from f of xy plus fx delta x to f of xy plus fx delta x plus fy delta y, changed by fy delta y. So when I'm integrating with respect to x, I'm going to be integrating along this interval, okay? And then I'm going to be integrating back along this interval. Now, both of these intervals have the same length, but one of them goes to the left and one of them goes to the right. On the one that goes to the left, the values of f of x are pretty much the same as they are down here, but they've changed because f is changing in the y direction. So that the part of the integral I get along here is going to be whatever the length of the interval is times fy delta y. Now I can write that out. I could call this path, I think your book uses C1, C2, C3, and C4 for the four segments that make up the path, make up the closed path. Okay. the difference here, f of xy on C2 is approximately Fy delta y greater than it is on C1. That's what we just established, okay? So when you subtract this integral from this integral, basically your difference for any values of x and y is going to be Fy delta y. And since the part that has the f of x that includes the Fy delta y is the one you're subtracting, you're going to have negative Fy delta y, okay? And of course, that's got to be, I want to rewrite these just a little bit because I should have put the dx in here. The integral over C1 is implicitly with respect to x. So the difference of the f of xy here minus the f of xy here is going to be negative your Fy delta y. And the distance over which you're integrating is delta x. Okay? Does that make sense? Something you should ponder. Okay. Similarly, between this part of the path and this part of the path, the function is basically about fx delta x greater here than it is here. I've got a minus on that and shouldn't have. Okay. Now it's greater on the part where you're integrating in the positive y direction, right? Between C1 and C2, the function is assuming, let's assume fx and fy are both positive, so that value is greater here than it is here. It's greater on the part of the interval where you're integrating in the negative direction. Okay? In other words, you get a negative Fy delta y here because the plus Fy delta y is part of this integral, and the plus Fx delta x is part of this integral in the y direction, part of the integral over C2 and the integral over C4. Now, there's one thing I wrote that's incorrect here. It's really plus the integral over C2. I put a minus there to emphasize the difference. It's really plus because the integral over, and I wrote C2 when I should have written C3. I hope that didn't confuse anybody, and it might have. Okay, we're doing this interval and this interval. The horizontal interval to the right over the bottom of the rectangle, the horizontal interval to the left over the top of the rectangle. Again, the difference in the value of f is basically Fy delta y. The difference is because this one, the top of the thing has moved in the y direction relative to the bottom. Okay? The integral over C1 plus the integral over C3. The integral over C3 is in the negative direction. So if you parameterized C1, C2, C3, C4, your parameterization would go, if T is your parameter, T is increasing on C1, it's going to be decreasing on C2, which will effectively make this a negative. Okay. I don't want to go too much into detail. I get into all the symbols and everything. Half of you will go blind and the other half will go insane if they do that. Okay. And I don't want that to happen. A little insanity is okay, but I don't want anybody to go blind. All right. Uh, the upshot of this is it's the integral around the whole path C, which is C1 plus C2 plus C3 plus C4. This integral will approximately be equal to fx delta y delta x minus fy delta x delta y which is fy minus fx delta x delta y is like a double integral of fy minus fx over area. I'm just giving you a quick glimpse of that because we're going to do it in more detail with this. Now, do you understand what I just wrote down here? First of all, the integral will be this and this. And I've got my signs going. Okay, I have my signs right here, and then I got careless with my subscripts and messed it up here. You're going to have your fx delta y delta x from the two vertical segments, the one on the right going up, the one on the left going down. It's going to give you fx delta y delta x. Sorry, it's going to give you, fx delta y delta x. The other one's going to give you negative fy delta y delta x. So you're going to have basically fx minus fy times delta x delta y, which makes a certain amount of sense. But I'm not going to try to explain that yet. Okay. Now back to Green's theorem. Are you going to do the same thing with this expression? But I want to my board's getting just plain old sticky. I try to move it. I've got it. Seems tilted. I have a wood block to take care of that, and I can't find it. This might serve. Okay, that's got it more or less. Okay, sorry for the interruption. So now I want to look at this integral of p dx plus q dy over the closed curve, which will be it'll be this. Why do I only integrate P dx over C1 and C3? It's because there's no dy when you're integrating in the x direction. Y isn't changing. So dy is 0 on C1 and C3. Dx equals 0 on C2 and C4. So the integral of P dx on C2 would be 0. You'd only be left with the Q dy and so forth. I think everybody understands that. Now remember, just to keep it in context, this is the integral big F of x, y dot dr over that curve. Got that written pretty small up at the top here, but it's written bigger here, right? So you want to keep that in mind because problems you have are not necessarily going to say integrate P dx plus Q dy. Okay? They could very easily say integrate F, big F dot dr over this curve or over the interior of a region or whatever. Now, by what we've said, the integral of P dx over C1 and over C3, remember, they're going in the opposite direction, so your dx might have an opposite sign, okay? That's going to equal approximately negative Py delta y. Because at any point up here, and Py delta y delta x, obviously. The negative Py delta y is because on the upper part of the path, C3, moving to the left across the top of the rectangle, is where the difference Py delta y occurs. Now, whether Py delta y is positive or negative, that difference is going to occur where you're integrating in the negative direction, and you're going to have a minus Py delta y. Okay? And then you have a delta x. Well, negative Py delta y is the average value of the difference in P between this path and this path. Okay? You multiply that average value by the length of the interval, which is delta x. So I can even say that's the average value of the change in P from the lower to the upper edge. And it's the negative of this is. And this is the length of the interval. There you have it. You can make the same argument for the Q function. The difference between what you have on C4, what you have in C2 where you're going in the positive direction, what you have in C4 where you're going in the negative direction, is due to the fact that C2 is displaced from C4 by delta x. So it's the QX times delta x. He quantifies the average difference between the value of the function on C2 and the average value of the function on C4. Okay? And you multiply that by delta y. And I could make the same note. This is the average value of the change in Q from the right edge to the left edge. Actually, it's from the left edge to the right edge. And that's the length of the y interval when you're integrating along the vertical segments. We're integrating in the counterclockwise direction implicitly. Okay, so again, I'm just going to say that QX delta X delta Y minus PY delta Y delta X equals I'll write it this way, negative PY plus QX delta X delta Y equals, and I want to write it in the same order your book does, but just because looking at it, and I don't have it there anymore. Let me find it. It's just a question whether P or Q comes first when they state it in Green's theorem, and I don't want to confuse you on that. Okay, they got QX minus PY, which is what I was tempted to write. And of course, delta X, delta Y is your area increment, meaning then that this is double integral of QX minus PY over the whole region. Okay. Give you a minute, give you a couple of minutes to digest that, because that's a big deal. This is not a rigorous proof. To write it rigorously, you have to write out all the symbols, and you can read those in your book. But this ought to make it believable to you. And then you can read the symbols in your book with more understanding. And we don't have time for me to go through that at a reasonable pace. Okay, final statement here. You have a rectangle with horizontal and vertical sides, X in the horizontal direction, Y in the vertical direction. The values of P, which is the function that we're the part of our f of xy dot dr function that we have when we're integrating in the x direction, positive or negative. Okay. The values on the top differ from the values on the bottom due to the fact that the y coordinate on top is different than the y coordinate on the bottom. So the average value of the differences here will be approximately the rate at which the value changes as we move in the y direction times how far we move in the y direction. That's your py delta y. Okay? Because of the directions in which we integrate, which I explained earlier, we have a negative on that. Okay? And then on the vertical increments, the values on C2, the edge to the right, and the values on C1, the edge to the left, where we're integrating upward along C2 and downward along C4. The values on C2 differ from the values on C1 because C2 is displaced in the x direction from C1, which means that the difference in the values is going to be the rate at which the values change with respect to x as we move from one edge to the other, multiplied by how far we move, which is, in the case of q, qx dx. Okay? And again, only q is integrated along the vertical sides because p is integrated with respect to x, and x isn't changing on either of those sides. It's in a nutshell. You understand that? The rest kind of begins to make sense. Now, whether it makes sense or not, you got a formula. Okay? And if you can use that formula, you're going to be okay. If you understand this and can use a formula, you're going to be more okay. Okay, that'd be like the difference between a B and an A. Okay. Provided I ask related questions, which is entirely plausible. Haven't made out the exam yet. So
I'll get off, man. We're big kid.
we want to do the integral of x squared y dx plus 2xy dy over some closed curve. I'm not going to go through the details of setting up the parameters and stuff because I do want to talk about the next section, divergence and curl, which is fairly straightforward, but see. Okay, so we've got this. Nice, this is being of the form P dx plus Q dy. Now you could ask the question, there's a conservative field? Because remember what we're doing is we're integrating x, y, I plus q. So we're integrating, x squared y, I plus 2xyj dotted with dxi plus dyj. It's an f dot dr. F would be x squared yi plus 2xyj. And dr is dxi plus dyj. Okay? So you can test this to see if it's conservative. Okay? But the y derivative of this is x squared, and the x derivative of that's 2y, so it isn't. If it's conservative and it's an integral around a closed curve, you got zero and you don't have to use Green's theorem. Okay? There's a little stuff on the board here. Let me just clear it a little bit. Okay. Now, this is equal to the double integral over the region bounded by your closed curve. And it will be explicit about that in a minute. I'll give you a couple of examples. Okay. The integral of qx minus py with respect to a. And what's qx? Well, qx is 2xy and py is 2x. Now, these two integrals then are equal. So we could just write out the equality just to emphasize it. The integral over c of x squared y dx plus 2xy dy is equal to the double integral over r of 2xy minus 2x respect to area. Then I'll say where R is the region enclosed by C, provided R and C are nice. And I'm not defining nice, but the region has to be simple. It has to be a simple closed curve. The region has to be simply connected. It's not a simply connected region, then you got to mess with it a little bit, but you can usually simply do it. But you can usually do it. And I'm not getting into that, and I'm not going to test on that because not every course even includes this material at the end. Okay. So also just because of weather disruptions early in the semester and maybe one or two other factors, we're having to push pretty hard to get this done. So not going to test on the full detail, all the topology of everything and all that stuff. Okay. Okay. So what's an example of a simple closed curve? Well, what if it's a rectangle? If it's a rectangle, then you got to break it into 4 different parameterized pieces, right? It's probably easier to do the area. If it's a rectangle with sides parallel to the x and y axes, you just got to integrate from one x to the other, from one y to the other. Up here, you'd have to parameterize everything. It wouldn't be hard. It would be just a little bit tedious. Now, sometimes your function is such that you can do this integral and you don't have a clue how to do this one. Or vice versa. More commonly, you could do this one, but you don't have a clue how to do this. This is just some crazy function that you have no idea how to pull some kind of a integration by parts or trig substitution or, some bizarre thing, okay? But you know how to integrate this. All of a sudden now you know what the integral of this is, even though you didn't actually do it. Okay, that's pretty cool. There are a lot of things that we know the integrals of because of Green's theorem. Okay. And again, sometimes the line integrals is a royal pain in the behind. If the region is one, we can break into inequalities and integrate over. Okay, does that make sense? But that's the overview. So I want you to get your feet wet with that. Hopefully get those problems done for next time, although if you need, don't wait until Monday night to do 3 sections of vector calculus. Okay. Because another thing you're going to have this week is surface integrals, which might be the hardest thing in the course. Until you understand it, then it becomes pretty easy. It's hard to understand. You got to have good geometric intuition over regions of a surface and the ability to parameterize weird surfaces. I'm not going to let it get too weird, but so don't put this off. See if you can make these translations. And that's how it's done. It's simple. It's p dx plus q dy over bounded, qx minus py over an area. One other little trick that I'll mention, it's pretty neat. If you make up functions p and q, okay, such that qx minus py is 1, then you get the area of this region. Okay. Now, if this region is bounded by some weird curve that makes it hard to set up the inequalities, but where you can parameterize the curve, then what does this integral give you? Well, it gives you this, which is the integral of 1 with respect to area, which is just the area. So if you want the area of some region, you can make up any functions, q and p, whose difference is 1. And apply this. Now, if it's a region, if it's a weird enough region, you're not going to be able to do either. Well, there are more weird regions that you can't do either on than there are others, but the ones that you can do them on are really important. A lot of those regions, a lot of the regions you need for applications, really important for applications, are amenable to this treatment, okay? So take that for what it's worth. Check the examples in the book and get examples online. You can do, and as you know, you can let online do your homework for you, but they won't learn it. And the chances, and, indications are that you'll pretty well have that under control, and that's very good to see. Okay. Now, a little comedy relief. We'll talk a little bit about divergence and curl. And I've already told you what divergence and curl are. I'll write it down. Make sure I'm still recording. Okay, divergence of F, which is del dot F, it's a dot product. It's going to be a scalar quantity, okay? So divergence at any point is just a number. Seen the example of a radial vector field, where that vector field diverges from the origin. Okay? We've seen an example of a rotational field where the vectors circulate like in a circle around the origin. They gave you those examples last week. Hopefully you looked at them and thought about them a little. But if you at least saw them in class, you'll help jog your memory when you see some of the pictures in the book. Okay? Okay, before I do a couple of examples, I'm going to diverge from my point right now just for a minute. I was double checking something I was doing for physics. I don't do that often, but I went to search because it was late, hadn't had enough sleep, and I was turning things around a lot, and I wanted to make sure my signs were right and everything. It was in physics, don't remember what it was. But I went and found it had to do with RLC circuits. Okay. And I searched and it showed me this neat graph and stuff like that. And I got what I wanted. Okay, it's a plus sign, and, that's all but I remembered the picture. Then I just kind of flipped through the physics text, which is an OpenStax text, and found exactly the same picture. AI was just quoting our physics text. And I'm sure it just quotes this Mullen-Grubel calculus text all over the place. Because it's free, it's open source, it's easy, and it's reliable for the most part. I haven't caught it in many errors. I've thought it made errors, but it was usually me. Once in a while, I felt like I needed to straighten them out, and I was right. But rarely. Okay. And, the authors know way more than I do. Okay. Just wish well they're careful with their editing and stuff like that. But I like what they have. Okay. So, okay, well, the divergence of F, okay, fairly simple function there. Well, divergence of F is del dot F, which is, to write it all out, partial respect to xi plus partial respect to yj, not done yet, plus partial respect to z, k, dotted with x squared yi plus the square root of yj plus yzk equals, well, I've got my i's and my j's kind of lined up here where I can easily see partial with respect to x of x squared y is 2xy. Partial with respect to y of square root of y is 1/2 square root of y. Partial with respect to z of yz is y. No i's, j's, or k's. I dot I, j dot j, k dot k, I'll give you one. So, well, that's pretty much it. Extra divergence. Okay. Let's do a curl. You notice that I've got the arrow over curl. Because I started to say divergence gives you a scalar. That's exactly what we got. Curl gives you a vector. Okay. So at any point, the divergence of a given function is just a number. Curl is a vector. It's going to have, in general, three components. Maybe you're confined to a plane, so maybe it'll only have two, but in general, it'll have three components. Okay, so the curl of, I don't want to do the curl of this function. And I'm going to do a curl of kind of a simple function here. Well, we're going to do a curl of xy squared I minus xzk. So it's a cross product of your del operator with xy squared I minus xzk. I left j out just because that's going to give me a pretty simple expression for the curl, and I'm not going to have to use a determinant. I don't want to use up the space. Everybody's using the determinant to do the curl. Did that in your homework, that's fine. In this case, it's actually a little more efficient to just use the distributive law. Partial with respect to xi crossed with xy squared I is zero because I cross I is zero. There's no j. I cross k is negative j. So we're going to have negative zj and partial respect to xi crossed with negative xzk. It's negative xzk, so it'll be positive zj. Okay. Then partial with respect to yj has to be crossed with xy squared I, has to be crossed with negative xzk. That's easy. Partial with respect to yj crossed with xy squared I. J cross I, well, j cross I is k. And the partial with respect to y of xy squared is 2xy. So we get a negative 2xyk when we do partial with respect to j crossed with xy squared I. And the partial with respect to yj crossed with negative xzk is zero because xz has no y component. Xz is just constant with respect to y, so the j cross k is going to give us nothing. And then partial with respect to zk crossed with xy squared I, well, xy squared has no z, so you get nothing there. So you can immediately see you only get two terms, zk minus 2xyj. Now, Okay. The divergence of the curl, well, the curl is ZJ minus XYK. So what's del dot ZJ minus 2XYK? Work that out. Okay, I'm not going to actually write this out except for the result, which is very clearly zero vector. Why? Because what's del? It's r respect to xi, etc., right? Well, r respect to xi dotted with zj minus 2xyk is zero because there's no I. No I component, so you can't do partial respect to x of anything but the zero, right? Okay, partial respect to yj. Well, that means partial respect to yj dotted with zj. That's a partial respect to y of z. What's the partial respect to y of z? It's zero. Okay. And you don't do the partial respect to y of your k component because you're doing a dot product, and you should, that should get to be second nature if it isn't already. Okay. You should just be able to look at this and do the dot product in your head without having to write it all out. But write it out till you don't need to anymore. Okay. And then the partial respect to z times k dotted with 2xyk is zero because 2xy has no z. Okay. Now, are you surprised? I mean, I just made that up. How did I know that was going to work out? Well, I know that's going to work out because it always works out because the curl of the divergence of the curl is zero. Always. And that's really easy to do. You just write it out. Your book writes it out. I'll write out a little bit of it for you and you can finish it if you want to. I'm going to write down everything at once. And I got it written out with the crosses where I need it. So del dot del cross f. If f is x of ti plus y of tj plus z of tk or whatever, and sorry, just got stupid there for a minute. Hopefully I'll recover shortly. Okay, we'll call this the function f pi plus qj plus rk. So what we've got is del dot del cross f. Del cross f is a curl of f. Del dot del cross f is the divergence of the curl of f. Instead of f, we're going to write pi plus qj plus rk, where pq and r are implicitly functions of x, y, and z. Okay. Now we're going to do I, j, and k. We're going to do the determinant because It's more efficient when we have all three components to go ahead and do the determinant. When you've only got two components or in certain other simple cases, it can be more efficient to use a distributive law, but nobody's going to do that. So, okay, so this is del dot what? Okay, well, it's I times Rx minus QZ. It's J times PZ it was minus PZ minus RX J plus, I've got to get the signs right, it's going to get screwed up and my eyes aren't working right. K times, get too many RX and then hit QX. K times QX minus PY times K. I think those are right. And if they aren't, you can write them out more carefully than I just did. Okay? Think them through. Now, del dot means okay, that should be RY minus QZ. And that should be missing Y, and that should be missing. See, that's better. Okay, del dot. Okay, we're taking the partial respect to XI dotted with RY minus QXI gives you RXY minus QXZ. And then the partial respect to Y, J dotted with PZ minus negative PZ minus RXJ is going to be negative PYZ plus RXY. And that's wrong. R at RX is probably wrong. J, now we get RX. And for K, we get QX. Something's wrong, and I'm going to continue. And then partial respect to Z of QX minus PY is QXZ minus PYZ. My signs here are wrong. This should be plus PZ minus RX, which will make this plus and this minus. Now we see that I got RXY here and minus RXY here. I've got minus QXZ here and QXZ here. And I've got plus PYZ and minus PYZ here. It all cancels out. Does that make sense? You see how easy it is to write that out carefully if you're totally conscious, which I'm apparently not at this point. Okay? Because I kept writing things down wrong because I was trying to move through it fast, which was a mistake. Okay? I'm looking at something sideways there. So, but that's why the curl of the convergence is zero. Well, in the test for conservative field in that case, and you can read about that. And talk about it next time if you got a question of it. Okay. But the curl of a conservative field is zero. Okay.